Hello, welcome to a theatre time, first one for a very long time, without funny backdrops and green screen stuff, because we're in I use the digital, oh, I've done it again, I keep using that really bad swear, I don't know, we're in the shop, and because we've been doing electronic stuff with Arduinos in here, we will come back to that. We can justify being in here because we're talking about thyratrons. Thyratrons in theatre, they were, I hate to say it, epoch making, to sort of be posh and sort of rather Cambridgey. They were a new game. They altered the whole way we thought about lighting control. Absolutely fantastic devices. The development started about 1914 and they first appeared on the open market, I think, about 1928. Up until then, all the stuff we've looked at before, resistance dimmers, saturable reactors, we've missed out, auto transformers, etc. But they were all working on voltage control. The Thyratron moved the whole way of thinking. They gave up trying to control the voltage. Let's control the current. Let's say when we can pulse current. It's a current pulse device, just like the saturable reactor, not the saturable reactor, the silicon controlled rectifier. The thing is with Thyratron, because back then we didn't have solid state electronics apart from a few, so we had copper oxide diodes and things like that. It was all valves. And the Thyratron is, strictly speaking, a triode valve, although there are actually, certainly in theatre, there were cold cathode Thyratrons, but in theatre we used hot cathode Thyratrons, so there were 5 pins on the valve. 3 of which did the work, and the other 2 were to provide current for the cathode heaters. They're a hot cathode device. Thing with the Thyratron, very much like the SCR, there's a lot of similarities. With the Thyratron, once the current starts flowing, the grid has no effect. You can't turn it off except by stopping power to it. If they're running on an AC circuit, of course they pass through 0, 0, 0, 0, yeah, and they turn off then. And that's how they worked. By controlling the potential on the grid, you could decide when the arc starts, when they switch on, and they ionise their gas. They're a gas-filled device. They're not a vacuum tube. There is a low-pressure gas in there. They used various things. There's mercury vapour was used, argon, xenon, neon, the noble gases. And apparently for really high voltages they used hydrogen at immensely low pressure, but it's just designed to worry you. Hydrogen is actually quite safe. Don't worry about hydrogen. Pure hydrogen, as long as it's kept pure, is a safe substance. It's only when it starts mixing with oxygen or chlorine or something it gets out of hand. The first ones that I can find were developed by Yale in the United States. There might be others, but that's what I found, and I've been digging around a fair bit, thus remaking the video. Let's actually look and do the paper bit, and we'll do some drawings and look at kind of how this works, and then we'll come back for some stories about when they didn't. But I've already recorded that, so they're a different colour balance. Don't worry about it. I'll try and correct it, but probably won't. And these stories are apocryphal. I want confirmation on their truth or otherwise. Let's do the paper bit. This is going to be a really really fun because I can't write left-handed, and because of the arrangement of everything, yeah. Right, where do we start? We have a cathode, so that's going to be minus VE. I'm actually writing kind of at a really strange angle. We have an anode, that's going to be plus VE, obviously. Right, is that in shot? That's just about in shot. At least knows what the exposure is like. And in the middle we have a grid, which, hang on, there we go. This also has a heater, so that's heated with an extra low voltage to encourage the, and we're now going to use some AVE terminology rather than the correct terminology, to encourage the magic pixies to emigrate from the cathode. The grid is held negative. If the grid is negative, the magic pixies coming up here meet magic pixies sat on there, and now the magic pixies on there don't actually like to move, and they don't like the other pixies, so nothing happens. If you turn the grid off, you know, make the grid positive with respect to the anode, the thing will fire. And that's a description that was used at the time. It will fire, and you will get an arc that jumps from there to there. Full current flow. Wow, fantastic. At that point, the grid can't do anything. But because we're on an AC waveform, he says, looking for another bit of paper. Please be blank. It's not. One moment. Because it's an AC waveform, that's not a particularly good sine wave. Here is 0 volt. Every time current goes through there, the thyratron will turn off. And it won't work that way because it's a DC device. So you have another one. And we will see how that fits together in silicon controlled rectifiers later. Not today. Depending on where this is, if we knock the gate off there, it will conduct for that part of the cycle. If we knock the gate off here, it will conduct for that part of the cycle. If we knock the gate off here, it will conduct for that part of the cycle. It's a bit like pulse width modulation, isn't it? Except very slow and with a sine wave. That's basically how they work. It's exactly the same as a silicon controlled rectifier, except the gate control is different. You actually take the potential off the gate in order to encourage it to conduct. That is how thyratrons worked. There's been a lot of debate on the internet saying that actually no, they were only used to control saturable reactors, etc, 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 or autotransformers. They were also used at full power. Thyratrons were capable of handling incredible power. They got very big, but they were capable of controlling quite considerable current loads, and the bigger they were, depending on the filling gas, the less the volt drop across them, which could be quite high. They were just, yeah, they revolutionised lighting. They're fairly well load independent, certainly compared to resistance dimmers, and the saturable reactor, which, as we know, is somewhat load dependent, not as bad as a resistance dimmer. These things were fairly well load independent, so they don't really care what's plugged on the end, so long as there was something there to draw some current, they would strike. They were fully remote control, and they revolutionised lighting. And they didn't last very long because someone came along and invented solid state electronics. There's enough of that. Let's have a chat with a slightly better view about one of the disadvantages of them, I'll just mention the other disadvantage, of course, like everything at the time, technology weighed, and yeah, these things were heavy, and being made of glass, fragile. Let's change the view and have the stories. Right, so we've just mentioned hot cathodes, and I've just said that thyratrons come with a load of folklore about their problems. Hot cathode is so called because the cathode is heated in order to encourage it to emit electrons. When they're stone cold, they tend to be very, very, very reluctant to let go of their pixies. They won't. Fluorescent tubes are an example of hot cathodes still in use. So once they're running, the heaters come off. But you do heat the electrodes at either end of a fluorescent tube in order to encourage them to conduct to start with. And it's a very similar process in the thyratron, except thyratrons are a very high speed switch, so it switches off through the 0 point of the cycle. And the best story goes, and this is the first story I heard of Thyratron's local theatre in the 1950s or whenever. They were refitted. They had Thyratron dimmers installed, and in their wisdom they put the Thyratrons in the ventilating ducts. So in the summer, I can vouch for this. I've spent quite a considerable time working in that theatre, and I know exactly what it's like. It roasts in there. It's unbelievably hot. Goodness knows why. It's badly designed. So you turn the blowers on to try and cool the old dears down before they all die of heat exhaustion, and of course they don't cool down. They just complain about the draft, and you've got to turn it off, and then they complain about the heat. And you've got these things which rely on being heated in order to work. And you're now blowing millions of cubic feet of cold air over them every minute. And the story goes that in the summer, when you've got the heaters on, when you've got the fans on to cool the theatre, blowing cold air over the thyratrons became somewhat reluctant to go to full. May or may not be true. Of course, the other end is in the winter. You turn the heating on, you're blowing hot air through the theatre, through the heating ducts, and heating the thyratrons. They were getting overly hot, the cathodes were getting overly hot, and throwing their pixies around left, right and centre. They became very reluctant to go off. And if the temperature changed during a scene, you could actually see the lighting change along with the temperature. I would love to know if these stories are true. That's the story I've heard in most detail. I would love to know if these stories about thyratrons and their temperamentality in heat is true. I would love to know. So please comment if you've got real on-hand live experience of thyratron valves and their weird ways, if their weird ways actually exist. We want this story either confirmed or, it's either bunked or debunked, I suppose. If you don't debunk something, you bunk it, don't you? Yeah. I want it kind of either confirmed or denied that thyratron valves in theatres were temperamental under temperature change. What are we going to talk about next time? We've mentioned already SCRs. We're into the modern era then. We're talking about silicon-controlled rectifiers, monodirectional thyristor, bidirectional triac. And you probably know about them already, so that'll be a short one. And we'll see you soon. Hopefully, we'll see you soon.